Hello everyone, this is workshop 7, balancing chemical equations. So we have been working with compounds and looking at their empirical formulas versus their molecular formulas, but now we need to actually balance chemical reactions as they occur. You're going to have different types of reactions and you'll have to know the products that form and the proper way to balance said equations. Because remember, the most important rule, or one of the most important rules of the universe, energy cannot be created or destroyed, matter cannot be created or destroyed. And now what that means for us is that if we have some chemical reaction, iron plus oxygen becomes iron oxide, the atoms of iron and oxygen have to stay the same throughout the reaction process. You are not going to suddenly lose iron molecules and you're not going to suddenly create extra oxygen by the end of this. The subscripts associated with each of these compounds is not going to change. Iron by itself is just iron, oxygen has to be O2, and iron oxide in this form has to be Fe2O3. We are not going to change these subscripts. But if we got rid of our coefficients and everything was just 1, 1, and 1, we'd have 1 atom of iron versus 2 atoms of iron, and 2 atoms of oxygen versus 3 atoms of oxygen. And if we're not creating or destroying any of the atoms, then that is not balanced. That chemical reaction would not be correct, because while you have the right atoms involved, you're not adding random atoms and you're not getting rid of any of them. The numbers themselves are not balanced. And so that is where our coefficients come in. Coefficients are allowed to change depending on however the reaction needs to be balanced. The subscripts tell us how many of each atom that we have. That cannot change. This is always oxygen, this is always iron oxide, this is always lone iron. But the coefficients can change as much as they want, because all the coefficient is telling us is how much of that substance we have. We have 4 moles of iron here. We have 3 moles of oxygen, and we have 2 moles of iron oxide. I could easily change these numbers. I could double these quantities and make this 8, 6, and 4, and this would still be balanced. You have the correct number of each atom in this equation, and only the coefficients change. The coefficients could be whatever numbers you need them to balance the equation, so long as you are not changing the actual compounds or atoms themselves. And so now we have to be able to look at a chemical equation, a skeletal chemical equation essentially, one without coefficients, and be able to balance it. When we have a certain amount of each element, how do we balance out this chemical equation to get our atoms balanced without physically changing the makeup of each compound that is in the reaction? So there are a list of steps on this first page of the worksheet, but I find it easier to follow along with an example as we talk through the steps. So for this first example here, they're telling us a reaction of C7H16 in the liquid form plus oxygen gas becomes, let me move this plus sign over so I can room, plus carbon dioxide gas and gaseous water. So this is a combustion reaction. An organic compound reacts with oxygen and producing carbon dioxide and water. But now we have to actually make this balanced. So this would be your step 1 if the equation is not given to you. Sometimes a problem might not give you the actual compounds in the equation like this. They might write out the full name of the actual compound. Remember, we went over naming compounds a few workshops ago, and so you might have to go back to those skills to be able to first write this skeletal equation as we have here. Other times, like in this example though, they're going to give you the skeletal form of your equation. So now once you have that skeletal form, now we have to go into balancing it. And the most straightforward way to do that is to make a table, organizing your information. So let's make a table below our reaction here, keeping track of each type of atom that we have present. We have carbon, hydrogen, and oxygen. So we're going to make a table containing carbon, hydrogen, and oxygen. And now we're going to focus on the number of atoms we have on the reactant side and the number of atoms we have on the product side. So now we have our table, we know what elements we're looking at, and so now we're just going to write down how many we have on each side. On our reactant side, we have 7 carbon atoms, 16 hydrogen atoms, and 2 oxygen atoms. While on our product side, we have 1 carbon atom, 2 hydrogen atoms, and you have to add up the atoms across the entire side of the reaction. It's not just based on one reactant or one product. So we have 3 atoms of oxygen. So now that we know how many of each atom we have on each side, we can focus on balancing our equation. It is best to start with the most complex compound first. Start balancing your more complex molecules and then go from there. If you're ever struggling to determine which compound is the hardest to balance, always remember you're going to balance your lone elements last. Those should always be your last step because those are compounds that you can put a coefficient in front of and you know you are only changing the amount of that one atom. If it's a compound that has multiple atoms involved and you put a coefficient in front of it, not only are you changing the amount of the desired atom, but you're also changing the amount of other atoms as well, and you'll have to start fixing it on both sides, balancing both sides of the equation at the same time. So always leave your lone elements for last. So in this case, we're going to start with our C7H16. So we want to balance our carbons first. If we have 7 on our reactant side and 1 on our product side, the least common multiple of 7 and 1 is 7. So if we need to have 7 on our product side, we're going to multiply carbon dioxide by 7. And notice, because carbon dioxide contains carbon and oxygen, 7 times 1, we balanced our carbons, but now 7 times the 2 oxygens, we have 14 right here, and 15 from the one in our water. But we're not going to focus on oxygen yet, because again, we have lone oxygen here. So instead, we're going to finish balancing the the C7H16. We have 16 hydrogens on the reactant side, 2 on the product side. The least common multiple of both of these would be to get 2 up to 16. We can multiply water by 8. 8 times 2 gives us the 16 that we need. But again, now we're doing 8 times 1. We have 8 oxygens here. And we still have the 14 from our carbon dioxide. So 14 plus 8, we currently have 22 oxygen on the product side. And this is why we saved our lone oxygen for balancing last. Because now notice, 2 and 22, you can get 2 to match 22 by multiplying by 11. And there's nothing else being affected when we put the 11 in front of the oxygen. Since oxygen is by itself, it's just 11 times 2, which is 22. We aren't touching other atoms like we were before when balancing the carbon dioxide and the water. And so this would be the final balanced equation. If you want to write a 1 in front of it for now, just as you're practicing to get comfortable with knowing that this is just one molecule, then you can. But the final answer would have nothing written here. If no number is written, we assume that it means 1. So whenever you're balancing a chemical equation, you write out the skeletal form if it's not given. If they give you the name form of it, you write out the skeletal equation, leaving space for your coefficients. And then we are making this table, keeping track of what atoms there are and where they appear on each side of the reaction, reactants versus products. There were 7, 16, and 22 for carbon, hydrogen, and oxygen. And we had to balance it with the 1 carbon, 2 hydrogen, and 3 oxygen. And so we focus on the more complicated molecules first, our C7H16. And then once we balance the more complicated atoms of carbon and hydrogen, we go back to our oxygen that was by itself. Our lone atoms get balanced last because, as we saw here, we just had to multiply by 11 and nothing else got affected. We were able to change the amount of oxygen on the reactant side as we needed without messing up any of the other atoms and having to continue to balance our equations. And so those are the steps that you're going to follow for all balancing reactions. And so if we're good with this example, I just want to see, there should be one more practice example and then we can go into practice problems. Yeah. So this is just with atoms. Carbon atoms, hydrogen atoms, oxygen atoms. But of course you can't forget that polyatomic ions also exist. Make sure that you're getting comfortable with naming, being able to identify the different polyatomic ions, memorizing their names, their charges, being able to write out the formula if you're given a name, and vice versa. But now we have the reaction of lead. Remember, NO3 is going to be nitrate. So lead nitrate, aqueous, plus sodium chloride, also aqueous, becomes sodium nitrate, and lead chloride. So again, they gave us the skeletal equation here. Oh, but they also gave us text in the top, so they might not have given that to us otherwise. They said an aqueous solution of lead 2 nitrate and sodium chloride are mixed, so you'll be able to know your reactants from that. The products of the reaction are an aqueous solution of sodium nitrate and solid precipitate of lead chloride. So if the reaction was not given, you would have to write it from the text. And so now we're going to do the exact same setup as we did with the C7H16. We are still going to make a table keeping track of all of the elements that we have. But we're not going to write it like this. Last time we had to write out all of the individual atoms because we were only working with different types of atoms. And so you might be inclined to separate nitrate into nitrogen and oxygen, but there is no need to do that because nitrate stays as nitrate on the reactant and product side. So long as a polyatomic ion stays as that polyatomic ion in solution from reactant side to product side, you can treat it as its own atom. It is its own ion, its own species, and so we are going to balance the entire thing. We're not going to try and balance the separate nitrogen and oxygen, which will then make balancing a little bit easier because now we're not keeping track of 5 different atoms. Now we just have our 4 groups. We have our reactants and our products. And so again, now we just count up how many of each we have on the reactant side versus our product side. We have 1 lead, 2 nitrate. Remember, polyatomic ions go in parentheses, and the amount is tracked by the subscript outside said parentheses. Sodium 1 and chlorine 1. Now for our reactant side, we have 1 lead, 1 nitrate, 1 sodium, and 2 chlorine. So, skeletal equation, filling in our table. And now, again, we look for the more complex substances. In problems like this, it's not immediately obvious which one is the most complex, and so it doesn't hurt which one you actually start with. I would recommend starting with your polyatomic ions first, but outside of that, it doesn't really matter which one compound we start with, either the lead nitrate or the sodium nitrate. But we could also start with the lead chloride. It really, in this problem, doesn't matter as much where we start with our balancing. Lead is already good, so let's balance the nitrate. We have 2 nitrate on our reactant side, and we have 1 nitrate on our product side. And so to balance this out, we need 2 nitrate. Multiply the entire compound by 2, and so we have 2 nitrate on each side, but this also changes the amount of sodium we have on the product side. Now we have 2 sodium as well as 2 nitrate. So now let's look at our sodium and our chlorine. We need 2 sodium on our reactant side and 2 chlorine on our reactant side, and sodium chloride is a compound that we have. If we put a 2 in front of the sodium chloride, we are affecting both the sodium and the chlorine, making them both 2. And so now all of our atoms are balanced. So for this one, it's 1 lead nitrate plus 2 sodium chloride becomes 2 sodium nitrate and 1 lead chloride. The steps you use to balance your equations are always going to be the same. The hardest part is definitely writing out that skeletal equation, making sure your compounds are correct, and then paying attention to just what each side is doing. Paying attention to what changes you are making. If you are changing one atom, make sure to focus on if you're changing more than one atom at a time, just by making one change. We changed our sodium nitrate from 1 to 2, but that also changed, well, we changed our nitrate from 1 to 2, but that also changed our sodium from 1 to 2. And so when we move to our reactant side, we would put a 2 in front of both the sodium and the chlorine. Both changed from 1 atom to 2 atoms, and that's exactly what we needed to balance the equation. Starting with the first 4 problems on the worksheet, 2, 3, and 4, they give you the equation outright, and 1, they do not. They actually give you very little information. They just tell you it's the combustion of isooctane. They tell you it's CH18, but remember, combustion is always reacting an organic compound with oxygen to produce carbon dioxide and water. That reaction is never going to change. Anytime you see combustion, 3 of the 4 parts should be the same. Oxygen is a reactant, carbon dioxide, and water as your products. The only thing that really changes is this starting species, and that would be given to you. And so I'm going to create a table over here, and we're just going to reuse this table for each of the reactions. So, starting with 1, combustion of isooctane. A lot of combustion reactions are also going to have similar, if not the same, elements to be working with: carbon, hydrogen, and oxygen. So we're looking at carbon, hydrogen, and oxygen. On the reactant side, we have 8 carbon, we have 18 hydrogen, and we have 2 oxygen. And on the product side, we have 1 carbon, 2 hydrogen, and 3 oxygen. These numbers for the product side are also going to be pretty consistent, if not the same, for a lot of combustion reactions, since you're always making that carbon dioxide and water. But now let's look at balancing it. Just like before, we're going to leave our oxygen for last. It's by itself, and we're going to focus on that isooctane. We have 8 carbon at our reactant side, and we have 1 on our product side. And so, the way to balance this, we need 8 on our product side. We're going to multiply our carbon dioxide by 8. And so that will give us 8 carbon, and that's going to change the number of oxygen. I'm actually just going to wait to put that down. Let's balance our hydrogens first. 18 hydrogens on our reactant side, 2 on our product side. And so we need to bring the 2 up to 18. 2 times 9 gives us 18. And so now our carbon is balanced, our hydrogen is balanced. Let's focus on our oxygen to see what we need to do. 8 times 2 is 16. 9 times 1 is 9. 16 plus 9, we currently have 25 oxygen on our product side. Now, this is what makes combustion reactions usually your more difficult, if not your most difficult, types of reactions to balance. Oftentimes, you are going to have odd numbers involved. The example that we used before, we got a little bit lucky. It was a little bit nicer of a combustion reaction, and so there were no odd numbers, but this is a much more common occurrence. So, when you have odd numbers, an odd number versus an even number, it's harder to know how to balance it because we are trying to not have fractions. You can easily set up a fraction to get the 2 up to 25, but you can't have half of a molecule. You cannot have half of an oxygen molecule, and so we can't leave fractions in our final answer. but we can still use fractions when going through the calculations for it. We need to bring 2 up to 25, and if we currently have 2 oxygen, we can use a fraction that will cancel out the 2 and leave us with just 25. 2 oxygen times 25 over 2 would give us 50 over 2 oxygen atoms. And 50 over 2 is equal to 25. And so if we multiply this by 25 over 2, this would give us the correct amount. 25 over 2 times the 2 oxygen we have would give us 25. But we can't leave it in this form because, again, it's a fraction. And so just like before, we had 2 oxygen, and so we multiplied it by some fraction over 2 to cancel them out. We're going to do the same thing, but with the entire equation. Based on, I forget the name of the rule, but in algebra, whatever you do to one side of the reaction, or equation if we're using math, whatever you do to one side of the equation, if you do the same to the other side of the equation, then the equation still works. The sides are still equal to each other, so long as you copy what you're doing on each side. The same thing works here. If we want to get rid of 2 in the denominator, the easiest way to get rid of the denominator is to multiply by the same number. If we multiply 25 by 2 over 2, we see what happens. 2 will be on top, 2 will be on the bottom, they cancel out, you'd be left with just 25. And so that's exactly what we're going to do with our entire equation. If we multiply this entire problem by 2, that fixes our problem here, because it will be 25 over 2 times 2. The 2's cancel out, and you're left with just 25, and that is what we're looking for. But the only way to multiply this fraction by 2 to get the 25 by itself is if we multiply the entire equation by 2. Because if we don't do that, then the equation is no longer balanced. We would only be affecting one species rather than the entire thing. We can't only multiply the oxygen by 2. And so if we're multiplying our entire equation by 2, then that means we have 2 of our isooctane. The 25 over 2 becomes just 25. This was originally 8, so now we have 16 carbon dioxide. And this was originally 9, so now we have 18 carbon dioxide. Anytime you have odd numbers like we did before, we had 25 versus 2, you can turn this into a fraction, larger number over smaller number, 25 over 2, because that would cancel out to give us just 25. But then once you have that fraction, you again have to multiply everything by the denominator of your fraction to make sure you only have whole numbers. You cannot have 25 over 2 oxygen atoms because that would imply that you have half of an oxygen molecule. You physically cannot have half of an oxygen molecule, so you have to eliminate that fraction by taking the entire equation and multiplying by the denominator, in this case, 2. Combustion is usually the hardest problems you have to balance because of the occurrence of odd numbers. And just to check that this is still balanced, we could actually change all of these numbers since we just put a coefficient in front of everything. We have 16 carbon, 36 hydrogens, and 25 times 2, 50 oxygens. We have 16 carbons, 36 hydrogens. This would be 32 plus 18. You would have 50 oxygens. Our balancing works. And always check for that at the end of your reaction. Make sure all of your numbers are balanced. Make sure there's an equal number of atoms on both reactants and product side. So that is problem 1. Now on to problem 2. So we have lead nitrate again, reacting with iron chloride to become iron nitrate and lead chloride. So we have nitrate on the reactant side and nitrate on the product side. So remember, we're not going to break it down into nitrogen and oxygen. We're going to leave it as nitrate. So we are working with lead, nitrate, iron, and chlorine. We have on the reactant side 1 lead, 2 nitrate, 1 iron, and 3 chlorine. On the product side, we have 1 lead, 3 nitrate, 1 iron, and 3 chlorines. Oh, I'm sorry, I wrote the problem wrong, it looks like. Let me just check. Yeah, this is supposed to be a 2. So we actually have 2 chlorines on the product side. Sorry about that. Yeah, so 1 lead on each side, 2 nitrate on the reactant, 3 on the product, 1 iron on each side, 3 chlorine on the reactant, 2 on the product. There we go. So now again, we're looking for the harder species to balance. And so we can start with really any of these reactants. Even though it is an even number with an odd number, try to avoid fractions as much as possible. Just try to balance it out with whole numbers first. Fractions are really a kind of like last resort to make things work. So instead of trying to make fractions out of this to make these balance out, we're just going to do least common multiple. 2 and 3 can both be multiplied up into 6, and so that's exactly what we are going to do. If we have 2 nitrate on the reactant side, we can multiply our lead nitrate by 3, and that would give us 3 times 2, 6 nitrate. And we can do the same thing here. We can multiply our iron nitrate by 2. 3 times 2 would again give us 6. And now we have to focus on what we changed by adding these coefficients. It's lead nitrate, so now we have 3 lead on our reactant side. And it's iron nitrate, so we now have 2 iron on our on our product side. So our nitrate is balanced, but now we've unbalanced our lead and our iron. But instead of trying to balance those back out, we can do what we did with the nitrate with the chlorine as well. We had 2 versus 3, and so we found the least common multiple. Now we have 3 versus 2. We are again going to find the least common multiple, which is again going to be 6. So if we have 3 chlorine on our reactant side, we're going to multiply by 2. And that will give us 6 chlorine. If we have 2 chlorine on our product side, we multiply by 3, and that'll also give us 6 chlorine. And now we have to see what we've changed by adding these coefficients. We now have 2 iron on our reactant side, and we now have 3 lead on our product side. By fixing only the nitrate and the chlorine, we also balanced our lead and our iron. After we balanced the nitrate, you could have gone and balanced the lead and balanced the iron separately. You didn't have to focus on the chlorine. Notice you still would have gotten the same answer, because by changing the chlorine, we changed our lead and our iron. Same thing would have happened if you focused on your metals, and then that would have just had an effect on your chlorine to again balance it out. The order itself is not always important. There's a few different ways you can go about balancing these equations and still get the same answer. Following a different order of steps is not necessarily always a bad thing. It's really just paying attention to trying to do the more complicated species first, to try to get those out of the way, and focusing on these lone species last, since those will be, they have the most freedom in a sense when trying to balance. You know you're only affecting one species, not every single atom involved in the problem. So all of our elements are balanced, 3 to 3, 6 to 6, 2 to 2, and 6 to 6. And so this would be our final equation. So now on to the third problem. We have another combustion reaction. Organic compound plus oxygen is becoming carbon dioxide and water. So we are once again working with carbon, hydrogen, and oxygen. We have 6 carbon, 14 hydrogen, and 2 oxygen. And again, we have 1 carbon, 2 hydrogen, 3 oxygen. Similar setup. We're going to balance our organic compound first, our C6H14. 6 carbon on the reactant side, 1 on the product side. We're going to multiply our carbon dioxide by 6. And again, we're going to wait to change the oxygen. If you want to put an oxygen number down, you can. I just like to wait because I know that in a combustion reaction, I'm going to end up changing it twice, and so I'd rather just wait till the end when I'm done fixing things. 14 hydrogens versus 2 hydrogens. We're going to multiply our water by 7. 7 times 2 is 14. And now we can focus on our oxygen. 6 times 2 is 12. 7 times 1 is 7. We have 19 oxygen currently. And so again, 2 versus 19, not a very clear way to go about fixing it. And while here we were able to do cross multiplication because we saw it appearing on both sides of the problem just once. You know, we did 3 and 2 because we had just nitrate and just nitrate. We did 2 and 3 cross multiplying because we had just chlorine and just chlorine. Because oxygen is split up between the carbon dioxide and the water, we can't do any cross multiplication like that. We can't just say, like, we can't find the least common multiple of these two. I think that would be 38. We can't just use 38 to figure out where we're going because we'd have to somehow split it up between both of our products here, and that would be a lot more complicated. So instead, we go back in with making a fraction based on our table. 2 versus 19. If we have 2 oxygen here and we want that 2 to cancel out, we multiply it by 19 over 2. 2 oxygen divided by 2 will cancel. This is currently 19 oxygen atoms. But if we have a fraction, we cannot say that this is a final answer. So instead, we have to get rid of that fraction somehow, and we're going to multiply the entire equation by 2. So 1 C6H14 becomes 2. 19 over 2 times 2. Denominator and numerator cancel out. You are left with just 19. Those completely cancel to give you 19. 6 will become 12, and 7 will become 14. And to check that everything's still balanced, we have 12 carbon, we have 28 hydrogen, and we have 38 oxygen. And now we have 12 carbon, 28 hydrogen, and 24 plus 14, we have 38 oxygen. So this is correctly balanced. All of our atoms are equal by the end of our reaction. So now on to our last one. We have calcium hydroxide reacting with, they don't give us a state, so I'm going to say it's phosphoric acid. That becomes calcium phosphate and water. I'm going to say this is an acid-base reaction since no states were given. So, now in this case, we have a few different polyatomic ions, but pay attention to which ones remain and which ones don't. The phosphate stays as phosphate. We go from phosphoric acid to calcium phosphate, so we can leave that as it is. So we have calcium. But the hydroxide does not stay as hydroxide. There's no hydroxide in our product side, so we can't write that as an ion itself. We have to balance it as separate oxygen and hydrogen. So we have calcium, oxygen, hydrogen, and we have phosphate. If it stays the same on both sides, you can keep it, but if it breaks down, then you cannot balance it as an ion. You have to balance it as separate atoms. So on our reactant side, we have 1 calcium. Remember to distribute the subscript. So we have 2 oxygen. We have 1, 2, 3, 4, 5 hydrogens, and we have 1 phosphate. While on the product side, we have 3 calcium. We have, since these oxygens are part of the phosphate, we're just going to say that we have 1 oxygen, we have 2 hydrogens, and we have 2 phosphate. Again, a little bit harder to know which one to start with. You can either start by balancing the calciums, or you can start with balancing your phosphates. Both would probably be a good starting point. I'm going to start with the calcium. We have 1 calcium on the reactant side, and we have 3 on our product side. And so we're going to multiply this by 3 to bring up our 1, 2, 3. And now that is affecting the hydroxide, and since there is no hydroxide here, we have to see how it affects the oxygen and how it affects the hydrogen. We currently have 2 times 3, we're going to have 6 oxygen. And now these 3 hydrogens are going to stay the same, but now we have 2 here times 3, we have 6, and so we're going to have 9 hydrogens here. The 3 from the phosphoric acid do not get affected. It is only the 2 here that get affected by this 3. So that is balanced. And so now, if this is balanced, again, we balanced our calcium. Next hardest thing would probably be our phosphate, so let's go on to that. If we have 1 phosphate in the reactant side and 2 on the product, we can multiply our phosphoric acid by 2, and that will give us 2 here. In phosphoric acid, there's phosphate and hydrogen, so now we have to see how this 2 is affecting things. Our 6 here stays the same since we didn't change this coefficient, but now it's 2 times 3, we also have 6 here. So now we have 12 hydrogen. And so while the numbers before looked a little messy with the odd number of hydrogens and a lot of different numbers going on, it's now a lot easier to balance this out. We focus on our harder species, the calcium and the phosphate, and now we have 6 to 1 and 12 to 2 with a water right here. 2 hydrogen and 1 oxygen. We need to multiply this 2 by 6 to get 12, and we need 1 times 6 to get 6. So we multiply our water by 6. That balances our hydrogens to 12 and our oxygens to 6. And this is why we say do the harder species first, because a lot of times it ends up making what looks more complicated parts of it become easier. By focusing on the harder parts, it's often that you start untangling the problem a little bit more, and by the time you get to your odd numbers or you get to these species that seem really off, they're no longer as off as they originally were. Maybe the odd numbers are completely gone like we saw here, and a lot of times it just becomes easier to balance. Now these last 3 problems have not given you the skeletal form. They're expecting you to be able to write it out yourself. And so, as always, practice your naming rules, naming ionic compounds, molecular compounds, your acids, and just getting very comfortable with naming a compound just from the written name itself. So, number 5, write the balanced equation for the reaction that occurs when solid lead 2 sulfide reacts with aqueous hydrobromic acid to form solid lead 2 bromide and dihydrogen monosulfide gas. So, starting with our reactants, solid lead 2 sulfide is reacting with aqueous hydrobromic acid. So lead, its symbol is Pb. It tells us it's lead 2, so it's right in the charge now. Lead 2, so plus 2 charge. Sulfide would be sulfur, so Pbs. Sulfur is in the oxygen family on the periodic table, which has a charge of -2. And so this compound is already balanced. A plus 2 charge versus a -2 charge, everything is balanced. And if they give you a state, make sure you put that state in the actual equation itself. You need that there for it to be correct. If you're given an equation and it doesn't have the state written next to it, that's fine. But if you are writing an equation out and they either tell you the state or you know that it's supposed to be a solid, liquid, or aqueous, depending on your circumstances, like if you know your solubility rules or if any other information is provided, you have to input them. So we have our solid lead 2 sulfide reacting with hydrobromic acid. Hydro tells us it's a binary acid, so we put an H, and bromic would be bromine. and they tell us it's aqueous, so we put our AQ. Now we go on to our product side to form solid lead to bromide. So again, lead with a +2 charge. Bromide would be bromine. Bromine is a halogen, so it's always going to have a charge of -1, or almost always. Oh no, in terms of ions, it's always going to have a -1 charge. +2 charge in our lead, -1 in our bromine. We need 2 bromines to balance out the charges. 2 times -1 would give us -2, so +2 - 2 equals 0. So I'm going to write these a little bit closer together. So Pb, Br2, and they told us it's a solid. And dihydrogen monosulfide gas. We're seeing prefixes, we know it's a molecular compound. Dihydrogen, so H2. Monosulfide, sulfide would be sulfur, just like it was in the lead sulfide. Mono meaning 1, and it is gaseous. So PBS plus HBr becomes PBr2 and H2S. So now we can focus on balancing this. We have lead, we have sulfur, we have hydrogen, and we have bromine. We have 1 atom of lead, 1 of sulfur, 1 of hydrogen, 1 of bromine. We just have 1 of each atom on our reactant side. On our product side, we have 1 of lead, 1 of sulfur, 2 hydrogen, and 2 bromine. So the main balancing is going to be our hydrogen and our bromine. Let's focus on our bromine first. 1 on the reactant side, 2 on the product side. We are going to multiply our HBr by 2, giving us 2 bromines. And it works out that this is hydrobromic acid. That's going to give us 2 hydrogens as well. And that's all that is needed for this problem. This equation is completely balanced just by having the 1 coefficient. 1 lead sulfide plus 2 hydrobromic acid becomes 1 lead bromide and 1 dihydrogen monosulfide. Sometimes when you're balancing equations, you get questions that are more straightforward like this, which is always nice to see. It's always going to save some time. Now on to question 6. So, balance the reaction that occurs when aqueous hydrochloric acid reacts with solid manganese oxide, manganese 4 oxide, to form aqueous manganese 2 chloride, liquid water, and chlorine gas. So, reactants first. Aqueous hydrochloric acid. Hydro tells us it starts with hydrogen. It's a binary acid. Hydrochloric, which would be chlorine. So HCl, AQ. It's going to react with solid manganese, which is Mn, and it also has a +4 charge. Manganese oxide. We put our oxygen in. Oxygen family always has a charge of -2. We have a +4 and we have a -2, and we need this to balance. 2 times 2 would give us -4. And so this is MnO2. And they tell us that is a solid. Now on to our products. It forms aqueous manganese 2 chloride. So again, that manganese. Now it has a +2 charge. It became more negative. Manganese chloride, which means it's going to bond with chlorine. Chlorine's a halogen, has a charge of -1. And so just like here, 1 times 2 will give us -2, and that will balance out our equation, or our formula, sorry, not our equation yet. So it's MnCl2, because of the -1 charge, and we need 2 of them to balance out the charge of our manganese. It produces aqueous manganese chloride. It produces liquid water, so H2O, with the liquid next to it, and chlorine gas. Careful with chlorine. Remember, it is one of your, fix that, Chlorine is one of your 7 diatomic elements. You have to have those diatomic elements memorized, because if I were to write just this, it would not be correct. Chlorine does not exist by itself. Chlorine exists as Cl2. I'm starting to tilt upwards a little bit. Sorry about that. Yeah, because chlorine is one of your 7 diatomic elements, you have to write it as Cl2 when you're writing this equation. So now we can go about balancing. So the elements that we have hydrogen, we have chlorine, we have manganese, and we have oxygen. And a lot of our species are appearing in multiple groups. We have a few different elements appearing more than once in the equation. So let's look at what we have. We have 1 hydrogen, 1 chlorine, 1 manganese, and 2 oxygen, versus 2 hydrogen, 1, 2, 3, 4 chlorines, 1 manganese, and 1 oxygen. Chlorine by itself, so we're going to try to balance that last, or at least we're going to focus on this specific chlorine last, but overall we're just going to try not to focus on chlorine itself too much. Trying to keep that for last just because we know if we need to, we could affect that later. So let's focus on our hydrogens first. We have 1 hydrogen on our reactant side and 2 on our product side. And so if we put the 2 here, then we get 2 hydrogens, but we also get 2 chlorines. Now let's focus on our oxygens, 2 on our reactant side, 1 on our product side. So we're going to multiply this by 2 as well. Our water over here. Oh, I erased the one thing. So that will give us the 2 oxygen we need, but now we have 4 hydrogens on our product side. And now, since we have smaller numbers on our reactant side, this is a case where even though chlorine by itself, we don't have to worry about using that to balance it out. If we had less chlorines on the product side than the reactant side, we would just affect this chlorine. We put some coefficient here to make it balance, but in this case, it is smaller on the reactant side each time. We have 2 hydrogens versus 4 hydrogens, and 2 chlorines versus 4 chlorines. We have already multiplied this by 2, and to bring 2 up to 4, you would multiply it by 2. And so we're going to multiply this by 2 again. We multiplied by 2 the first time to balance out our hydrogens originally, and now we have to multiply it by 2 again, so 2 times 2 would give us 4. And so that would give us 4 hydrogens and 4 chlorines. And this would be our balanced equation. 4 hydrochloric acid plus 1 manganese oxide, manganese 4 oxide becomes 1 manganese 2 chloride, water, and chlorine gas. 2 water and 1 chlorine gas. So now on to our last problem. Write the balanced equation for the photosynthesis reaction in which gaseous carbon dioxide and liquid water react in the presence of chlorophyll to produce aqueous glucose and oxygen gas. So, for our reactants, it's gaseous carbon dioxide, so carbon and then dioxide telling us there's 2. It's gaseous. And liquid water, so H2O, with our liquid sign. They react in the presence of chlorophyll, and now we go on to our products. They produce glucose, which they give us the formula for, C6H12O6, and oxygen gas. No, this is aqueous, AQ, there we go, plus gaseous oxygen. There should be a formula that you're familiar with, not for this class specifically, but definitely for bio. I assume a lot of people are taking bio and chem at the same time. If you're not, that is fine. A lot of people also don't take them separately, but I know a lot of students tend to take them together, and so you're probably going to be seeing this reaction a lot, and you should be getting very, very comfortable with it. But for our intents and purposes, we just need to balance it. So our reaction has carbon, hydrogen, and oxygen. We're back to just our 3 elements, but now we're not doing combustion. We are doing photosynthesis, but it's a little bit similar. It looks almost like the reverse of a combustion reaction. An organic compound and oxygen are formed from carbon dioxide and water. We have 1 carbon, we have 2 hydrogen, and we have 3 oxygen on our reactant side, and we have 6 carbon, we have 12 hydrogen, and we have 8 oxygen on our product side. Just like a combustion reaction, we're going to focus on our oxygen last because we got that oxygen by itself if we need it. 1 carbon on our reactant side, 6 on our product. We're going to multiply our carbon dioxide by 6. So now we have our 6 carbon. 2 water on our reactant side, 12 on our product. We're also going to multiply the water by 6. That would not give us 6, that would give us 12. There we go. And now to add up what we have 12. We have 12 oxygen from our carbon dioxide, and we have 6 from our water. So we have 18 oxygen on this side. And so now, they're both even numbers, so we don't need to utilize fraction in this case. It's just going to be a little bit trickier to know how to multiply this to get from 8 to 18, because there's not a clear number involved, but we have this low in oxygen. So the main thing to focus on is that 6 of these oxygens are coming from our glucose. That's 6 oxygens that we know are not going to be affected. So really, we can ignore the fact that there is 8 of them and focus on the fact that we have 2. And we could set this up like a math problem. We need this to equal, not 16, we need this to equal 18. We know that we have 6 to work with no matter what, so plus 6. And we have 2 from our subscript here. So x is the coefficient that we're trying to put here. We multiply it by 2 because we know we're getting 2 oxygens from our gaseous oxygen, and we add 6 to it because we know that 6 of them are going unchanged. They are staying the same from the glucose. So 2x equals 12, x is equal to 6. We multiply our gaseous oxygen here. I'll actually write out the steps a little bit clearer. 2x equals 12. By both sides by 2, and x equals 6. So we multiply our oxygen here by 6. 6 times 2 will give us 12, plus the 6 we need to add up to 18. So sometimes it just requires a little bit of algebra. We know we're trying to get to 18 oxygens. We know 6 of them are untouched, so that is our plus constant. That would be our constant, so plus 6 in this case. And we know whatever coefficient we're trying to multiply by is going to be multiplied by 2, take into account for those 2 oxygens. So our final equation is 6 carbon dioxide plus 6 water becomes 1 glucose and 6 gaseous oxygen. And this is the actual balanced equation that you're going to learn about when you are learning about plants and the exchange of oxygen and carbon dioxide that we share with them. That is the end of this workshop. If there are still any questions on the content that was covered in this recording, absolutely reach out to the Math and Science Resource Center here at John Jay to get more assistance. You can book an appointment yourself through John Jay Navigate, or you can go to the Tutoring Center on campus, room 1.94 in the new building, and someone at the front desk can help you book an appointment. You can book one-on-ones either in person or virtually, and there are plenty of tutors here who can help you understand the content better.